Hmm. Okay. I was just noticing that on Twitch there's a little icon that says excellent, and I think it means that the stream quality is excellent. So I don't know. I mean, it's possible that watching on Twitch is better than watching on Zoom. I don't know. Uh, right? Yeah, and perhaps OBS is taking priority over Zoom. Uh, mhm. All right. Well, let's get started. Uh, so uh, So today, we're going to pick up where we left off last time. Last week was week one, right? We began talking about what distributed systems are, and then we began talking about this notion of happens before, and we began to talk on Friday about how happens before is a partial order. In particular, it's this special kind of partial order, an irreflexive partial order. Uh, so. Um, let's recap a little bit from last time. I realized that we had a couple of quiz questions last week, and I never talked about what the answers to those quiz questions are. So we can do that now. Um, so let's look at what the quiz questions were last week. So we had a quiz every day last week, actually, but Monday the quiz was just a survey about office hours. So this is the first content quiz question that we had, which was, what is a distributed system? So I said, pick whichever, pick Martin Kleppmann's definition, which we talked about, or pick Peter Alvaro's definition, which we talked about, or your own interpretation. So, so what I was amused by in this is that some people answered the question by just writing like Peter Alvaro's definition instead of actually defining it. And some people, at least one person, just wrote Peter Alvaro. Like the definition of a distributed system is Peter Alvaro. Okay. But what I was actually going for here was for you to actually to write down the definition. So the Kleppmann definition is a distributed system is some collection of nodes connected by a network that is a node in this case could be thought of as a computer or maybe as some software running on a computer. So some collection of nodes connected by a network and characterized by partial failure. So that was the Kleppmann definition, which I like a lot. Peter's definition is a distributed system is a system that experiences both partial failure and unbounded latency. So unbounded latency is also a key piece of it, at least from our point of view. So that's what we were going for with this question, or some combination of those things, or something that highlighted the points that we discussed. Mostly that there's more than one computer involved, and that failure is involved. Then the other quiz question, which was from Fridays, we said, okay, so if you have two events A and B, we say A happened before B, under what circumstances? And so there should have been three parts to this, the three parts of the definition of the happens before relation. First part was if A happens before B on the same process, then we say A happens before B. A process is inherently single-threaded, we say. So if A happens before B in a given process, then A definitely happens before B. Another way for A to happen before B is if A is a message send and B is a message receive. A message can't be sent after it's received. So if A is a send and B is the corresponding receive, then we say A happened before B. And then the third part of the definition is the piece that makes it transitive. So we say, well, if you have some other event C, and we know that A happened before C, and we know that C happened before B, then we can put those together to say, okay, we know A happened before B. And the combination of these three pieces allows us to look at some large collection of events that happen on many processes that are communicating with each other via sends and receives, and come up with an overall picture of what we know happened before what. Those were the quiz questions last time. We'll continue with this quiz approach and have another quiz question today. But let's go on and talk about today's topic. Okay, so we just recapped the definition of the happens before relation. And we talked about how last time the happens before relation is a special kind of partial order, which is an irreflexive partial order. So the happens before relation, there's these three parts to it. If A happens before B on the same process line, or if A is a send and B is a receive, then A happens before B, or if those things are put together somehow. Then those are all situations where we know A happens before B. And this and so the set of all of the events in a system, there could be lots of other events here too. The set of all of the events in the system are ordered by this partial order. But the happens before order is it's a slightly weird partial order in that it's not it doesn't have what we call reflexivity. So a traditional or a standard partial order has these properties that it's reflexive, which means that for all so if it's a partial order of let's say it's a set S, together with a binary relation, that looks like this. So we're going to say for all A that is a member of S, reflexivity would say that A is less than or equal to A. Antisymmetry would say that for all A and B in this set S, if A is less than or equal to B and B is less than or equal to A, then A and B have to be the same. And then the last bit is transitive, which says that for all A, B, and C in S, if A is related to B in this way, and I should have an if here also, and B is related to C, then A is related to C. So those are the properties that are true of a partial order typically. But for this particular partial order, the happens before relation, it's not quite one of these partial orders because it doesn't have this reflexivity property. Because it wouldn't make sense in this case, because we would be saying that for all, instead of, so substituting in what we're talking about here, we're talking about events in this set of events, we would say for all events, every event happens before itself. And so we don't want to say that. And so this is actually not a true partial order. It's instead what we call an irreflexive partial order. So these properties are true for the happens before relation, but reflexivity is not. So you'll often hear people, including me, say this is a partial order. So I'm letting you know that you don't have to say, well, actually, it's an irreflexive partial order. It's fine to just say partial order, right? People will probably know what you mean. But what's an example of a partial order that actually is a true partial order? So here's one. So So set containment, or set inclusion, as it's sometimes called. So in this case, so again, a partial order it's a set together with a binary relation. So the set in this case is going to be all subsets of a set. For instance, let's say that we have the set A, B, C. And these are just any ABC, anything. So we could write down the set of all subsets of this. So what's the set of all subsets of ABC? Well, it would have to include the empty set, right? And then the set with just A, the set with just B, the set with just C, the set of A and B, A and C, B and C, and then all three. So there should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. So this set S has 8 elements, which can be ordered by set inclusion, or this relation. And so we can draw a picture of how those 8 sets are related, putting the empty set at the bottom and putting this set ABC at the top. So then, well, what sets are the empty set contained in? Well, the empty set is contained in everything. But we can put at the bottom these 3 singleton sets, A, B, and C, the set containing A, the set containing B, and the set containing C. And then one step up from that, we have all the sets that have 2 elements in them. So the set containing A is a subset of the set containing A and B, so I can draw a line from here to there. The set containing B is also a subset of the set containing A and B, so I can do a line there. And similarly, I can do a line from the set containing A to the set containing A and C, and then like this, and then like this. And then, of course, all 3 of those are subsets of the set containing A, B, and C. So I have this nifty lattice here, which is a kind of visual depiction of the set containment relation. So this is an example of a partial order that really is truly a partial order, as in it actually checks all the checkboxes, so it is reflexive. Because, like, say if you wanted to know, is this set A a subset or equal to this set containing A? Well, the answer is yes. So, and then that's true for any, if you pick any element of this set S and you ask, is it a subset to or equal to itself? The answer will be yes. And then the other 2 properties of antisymmetry and transitivity, they both hold as well. So we're not going to go to the trouble of proving that, but it's true. So somebody in chat asks, how does the set containing A relate to the set containing B and C? Yeah, so good question. So they're not related by the partial order. So a partial order doesn't necessarily relate every element in this set S to every other element in this set. That's kind of the point, in fact. Some things aren't related. So those 2 are not related by this particular order. Maybe you could come up with some other order that related them. I don't know. But this set inclusion order doesn't relate them. So that's an example of a partial order. Now, some orders are total orders, which mean that you can that means that you can compare every two elements in them. So what's an example of a total order? What's like a really, what's the simplest total order that you can think of? Or what's one that comes up a lot in everyday life? The integers. All right. So somebody suggests the integers, or even like the natural numbers, right? Um, so yeah, okay. Let's go with the integers. So, well, let's stick with the natural numbers just because I want to have a smallest one. So in this case, our set S is just the natural numbers, right? And the relation we can just say is the usual less than or equal relation on the partial or relation on the natural numbers. So then our picture is just going to be a straight line, right? It goes on forever like that. Notice how before this picture wasn't just one straight line, right? We had this lattice shape. And now we have a straight line because the natural numbers are totally ordered. And so every natural number is comparable to every other natural number. So that's a total order. So that's probably all I have to say about that right now. If this were a class about order theory, we could go into a lot more detail. But this is a class about distributed systems. So let's come back to happens before. So we said that there were these three pieces of the definition of the happens before relation, right? Let's just write them down one more time visually. So one event happens before another on the same process line, or if an event is a send and then it happens before its corresponding receive, or there's transitivity that can put those pieces together. Okay, so if you've got a bunch of events, you can use this definition to figure out, what happened before what. Or at least you could if you had an efficient way to compute what is in the happens before relation. So what we talked about previously, we looked at a set of events and we sort of computed by hand what was in the happens before relation for that particular set of events by just kind of looking at it. But what we want to do is actually come up with an algorithm by which a computer can straightforwardly compute what's in the happens before relation. And this leads into our next topic. So last week we talked about clocks. In particular, we mentioned a couple of different kinds of physical clocks, but we also talked about problems with using physical clocks. So what did we say the alternative to using physical clocks was? Logical clocks, yeah. So this is an entirely different notion of clock. Logical clocks don't tell us anything about the time of day, and they don't tell us anything about time elapsed. Instead, logical clocks only tell us about the ordering of events. So the simplest kind of logical clock that I am aware of is called a Lamport clock. And a Lamport clock is just a way of assigning numbers to events. So if you have an event, let's say event A, then its Lamport clock, which we write LC of A, it might be 3, for instance. So what do these Lamport clocks mean? Like, what does that number 3 tell you? Well, here's a rule. We know that if A happens before B, then the Lamport clock of A is less than the Lamport clock of B. So we say that Lamport clocks are consistent with causality. That means that if there's a causal relationship between A and B, or a potentially causal relationship between A and B, that is, if A happens before B, then we know that the Lamport clock of A is going to be less than the Lamport clock of B. So we're going to write down the rules for assigning Lamport clocks to events. So let's put some events down and then just try to assign Lamport clocks to them. So here's some events. All right. So here's the algorithm for assigning Lamport clocks to events. First of all, every process has a counter that's initialized to 0, an integer counter, or natural number counter. On every event, a process will increment its counter by 1. I'll go over here to write down rule 3. Rule 3 is what you do when you send a message. When sending a message, a process includes its current counter along with the message. And step 4 is what you do when receiving a message. This is the interesting part. What do you think happens here? What do you think you do when you receive a message? Yeah, so there's some good suggestions in chat, like take the maximum of the received counter and your own counter. Yeah, so what you're going to do is set your counter to the max of your local counter and the message counter. Plus 1. So recall that sending and receiving are both considered events. Yes. So, by the way, in some formulations of this algorithm, message receives don't get counted as events. So if you don't count message receives as events, you wouldn't have to do this +1 here. So if you've seen this before and it didn't have the +1, then that's why. That might be why. But we're going to be treating message receives as events for now. Later in the course, we might look at a scenario where message receives don't count as events. But and that's something when you're talking about events, step 0, right, is to decide what counts as an event, and that can be up to you, right? So it can depend really what you're trying to accomplish. But for us right now, we're counting both message sends and receives as events. So we have a way of assigning numbers to events now. So let's try it. So we have to give every process a counter, right? So it's going to start out at 0 for every one of these. Okay. So we say on every event, a process increments its counter. That's the rule. What does the counter become for this event here? Let's call these processes A, B, and C just to give them names. So on process A, we have an event here. It's a message send. What should happen there? Yeah, so this becomes 1 right here. All right. So here's a receive. So process B is receiving a message right here. Process B's local counter is currently 0. But this number 1 got sent along with the message. So you can imagine this message kind of consisting of 2 parts, right? One of those parts is going to be, you could call it the payload, right? The part that is actually the reason why a message is getting sent. And then the other part, you could call it the metadata, which is some additional data that accompanies the message. And in this case, the additional data that's accompanying the message is just this number 1. So the 1 shows up here. We take the maximum, right, of the local counter, which is 0, and the message counter, which is 1. And the maximum of 0 and 1, of course, is 1. And then we have to add 1 to that. So the counter here becomes 2. So then we've got another message send. So also this up here is going to change. I should have pointed out this counter up here for process A is going to increment to 1. So now this process's local clock is 1. This one changes to 2. So now we have a message send here. So what happens on a send? Or what is our clock number now? It should be 3. That's right. So this is 3. And this changes to 3 up here. The 3 gets sent along with this message over to process C. Now, we've received a message here on process C. What takes place there? Well, 3 is the number arriving on the message counter. 0 is the value of the local counter. The maximum of those is 3. So we set our counter to the maximum of those plus 1. So that's 4. And then here we have another message send. So this message send, we have to increment our counter because that's an event, right? So we have to increment our counter. And the 5 gets sent along here. Finally, we arrive over here at process A again. We compare our local counter, which is at 1, to the message counter, which is at 5. The maximum is going to be 5, and we add 1 to that. So the value of this, or the clock, the Lamport clock of this event becomes 6. So if you walk through and look at the Lamport clocks here, you'll see that this condition that we wrote down before is in fact true. So if A happens before B, then the Lamport clock of A is indeed going to be less than the Lamport clock of B. This was a pretty simple one. But what about the other way around? So we know that if A happens before B, then Lamport clock of, whoops, that should just be less than. LC of A is less than LC of B. So in other words, Lamport clocks are consistent with causality. That's what we said. But what about the other way around? So if LC of A is less than LC of B, do we know that A happened before B? So here's the last, somebody was asking to see this again. So here's the previous slide again, and I'm going to take a picture of it right now. All right. So back to that question. So we know if A happens before B, then the Lamport clock of A will be less than the Lamport clock of B. But if the Lamport clock of A is less than the Lamport clock of B, do we know that A happened before B? What do you think? Yeah, perhaps surprisingly, it turns out that the answer is no. So let's look at an example of that. So let's say that we have processes let's say P1, P2, and P3. And let's put some events up here. So let's say call this event A. Okay, and let's call this one event B here. So let's try to assign Lamport clocks to these events. Let's just see if we can do it. So every process starts out with its Lamport clock at 0. All right, so we have an event A here. This one isn't a message send or receive; it's just an internal event. But we're gonna count those too. Those count as events. So so the Lamport clock here is 1. Then here's an event, right, on process 2. Well, what's the Lamport clock of this event going to be? Right, that one's also going to be 1. So the number 1 is going to get sent along on this message as metadata. And it comes over here to process 3, where the current process clock is 0. The 1 and the 0 are going to get compared. 1 is bigger, so we'll take the maximum of the two, which is 1, and then this clock over here is going to become 2. Then we have another event, happens to be a message send, and because it's an event, we increment our clock. So that's the clock there is going to become 3. The 3 is going to get sent along with the message, and we arrive over here. We compare the 3 to our current process clock over here, which is 1. 3 is bigger than 1, so 3 is going to be the maximum. And then we add 1 to that, so the clock here becomes 4. This should have been changed to 3 over here. Then we have another internal event here, so the clock here is going to be 5. Let's come back over here. So on process 3, we're here. We want to figure out what the clock value of this event is. Our current local clock is 3, and we increment every time we have an event. So the clock there becomes 4. 4 gets sent along this message here. 4 gets compared with the local clock here, which was 1. 4 is bigger than 1. So the maximum of the two is 4, and we add 1 to that, so the clock here is 5. Then finally we have this event down here. It happens to be a message send. We increment every time there's an event, and a message send is certainly an event, so our clock here is 6. 6 gets sent along with the message. And down here, 6 gets compared with the current process clock here, updating my process clocks. 6 gets compared with 5. 6 is bigger than 5, and so the maximum of the two is 6, and 1 gets added to that, so the clock here becomes 7. So the two events that I kind of pointed out originally were events A and B here. So in this picture, A has a clock value, a Lamport clock value of only 1. So there's a great question in chat, which is, do we increment the counter if an event fails? So we actually haven't started talking about failure at all yet. But also, I don't know what you mean by an event fails. So when we start to talk about failure, we'll talk about what kinds of failures can occur. So a failure could include a process crashing. That's one kind of failure that we'll talk about. But another kind of failure we'll talk about is messages getting lost. So yeah, I mean, if you don't receive a message, right, then that event never happened as far as you're concerned, right? So this picture, what we're talking about here, we're assuming that all these events actually occurred. But we're going to talk a lot more about failure soon. Yeah, somebody points out that this counter should have been updated here as well. Sure. And then this should have been updated to 7. Okay, so the real question I wanted to ask was, look at events A and B here. So A has a Lamport clock of 1, and B has a Lamport clock of 5. And we got those numbers by kind of just blindly applying the steps that we talked about before. So those 4 steps of the algorithm that we had before, where we said every process has a counter that starts out at 0. Every time there's an event, a process increments its counter. When you send your current counter along with the message, and when you receive, your counter becomes the max of your current process counter and the one that you received plus 1. So that's what we did here. But we ended up in this situation where B's counter is a lot bigger than A's counter. But does that mean that A happened before B? If we look at A and B, do we know for sure that A happened before B? Yeah, so not by our definition of happens before, right? Um, so one way for one event to happen before another, right, is if they're just on the same process line, right? And that doesn't happen here because they're on different process lines. Um, or one has to be a send and the other has to be a corresponding receive, and that's not the case here either. Or they have to be in a happens before relationship by transitivity. But that's not the case here either. So there's no connection between A and B in terms of the happens before relation. The happens before relation does not say that A happens before B. And so uh, we have a situation here where the Lamport clock of A is less than Lamport clock of B, but it certainly does not mean that A had to happen before B. So the answer to this question, if the Lamport clock of A is less than the Lamport clock of B, do we know A happened before B? And the answer to that is a resounding no. So indeed, we only have one direction of this implication. We don't have both directions of it. So here's a trick for knowing whether one event on a Lamport diagram happened before another one. If you, like, for instance, if you want to know if this event, happened before this event, if you can reach the second event from the first event, then you know that that the first event happened before the second event. So, in other words, like if I wanted to know if this event right here, the first event at the top of P2, if I wanted to know whether it happened before this one, I just ask, okay, can I draw a line from there to there? And it turns out that I can. Likewise, if I wanted to know whether this event over here happened before this event, I can draw a line. And connecting up the pieces, I can see that I can reach the event. But that's not true for this A and B here. I can't draw a line that will let me reach A from B. So in other words, and to be very fancy about it, we can say that causality is graph reachability in space-time. So in this picture, you can't reach B from A. So you can't say that A happened before B, even though B's Lamport clock is bigger than A's. Questions about this? I'm going to look back in chat because I think some good questions went by while I was talking. Yeah, so okay, so somebody objected to my my claim that that the message metadata was different from the message payload because if the message gets lost, then the metadata gets lost as well. Okay, I mean, I don't know how you define the words, how you define the word payload, but I'm distinguishing between the content of the message and this extra piece of information that we're sending along with the message. So most of the time in this class, we won't be incredibly concerned with the content of the messages. In fact, we're going to be spending more of our time talking about this kind of metadata, like the counters that come along on the messages. Now, there might be opportunities to talk about the content of the messages because there are times when the content of the messages actually matters in terms of the algorithm that we're computing. But for this, for things like Lamport clocks, we don't care what these messages actually say. All right. I've been asked to mute somebody. I will see if I can do so. Either I successfully muted the person or they muted themselves. All right, so we know that this direction is true. We know that if A happened before B, then the Lamport clock of A will be less than the Lamport clock of B, and the other direction is certainly not true. So we say, although Lamport clocks are what we say, Lamport clocks are consistent with causality. So this is the consistent with causality direction. But it's not the case that if the Lamport clock of A is less than the Lamport clock of B, then A happens before B. And so we say Lamport clocks do not characterize causality. That diagram actually that I showed a minute ago, this one here with the example of A and B, where we saw that A does not in fact happen before B according to the happens before relation, even though A's Lamport clock is smaller. That figure is it's an example that's taken from a paper by Schwartz and Mattern. Which I think is from 1994. And the paper is called Detecting Causal Relationships in Distributed Systems. In Search of the Holy Grail. So Mattern was one of the people who developed another kind of logical clock that does characterize causality, unlike Lamport clocks, and that's called a vector clock. And we'll talk about that soon. But this is a really great paper. I actually recommend reading this rather than reading the original paper on vector clocks because this came out a little while later. And sometimes it's really better to read things that came out later because even the people who invented some concept, they don't necessarily know the best way to explain it, right, at the moment that they invent it. And they don't necessarily come up with the best explanation until sometime later, right? So vector clocks were invented in the 80s sometime, and then this paper didn't come out until 1994. But I think this paper does a really, really nice job of explaining the need for this notion of vector clock, which we're going to talk more about soon. Okay, but we're still talking about Lamport clocks, not vector clocks. So Lamport clocks. Well, okay, so we said Lamport clocks do not characterize causality. Well, okay, so what are they good for? Why would you ever want to use them? What do you think? Okay, so there's some suggestions happening in chat. So I want to give a kind of a mathematical argument for why Lamport clocks are still useful, even though they don't characterize causality. So we know that this part is true, right? We know that if A happens before B, then the Lamport clock of A is less than the Lamport clock of B. So I'll write that down again. Okay, so this is a logical implication, right? Um, we have something over here that's like the premise, and then we have something over here that's the conclusion. So this is a logical implication. What's something that you can always do with an implication? You can take what's called its contrapositive. So contrapositives say that if P implies Q, then not Q implies not P. So we can do that here. And if we do that here, this, by the way, this means not. So if we take the contrapositive of this thing up here, then we get, if it's not the case that the Lamport clock of A is less than the Lamport clock of B, then it's not the case that A happens before B. So that's the contrapositive of this thing that I wrote down at the top. Okay, so in other words, if the Lamport clock of A is not less than the Lamport clock of B, then we know that A did not happen before B. So that's what Lamport clocks can be used for. They can rule out things as not having caused other things. And that actually turns out to be really valuable. It lets us debug, right? It lets us say for sure, as somebody just said in chat, that some event did not happen before another. And that turns out to be really useful for debugging. So we're going to pause and do a quiz question for a few minutes. And I'll post the quiz question in chat. And I'll also share it on the stream. This should say quiz number 4 at the top here. So a fun thing about sharing this page publicly is that everybody gets to see as the responses come in. So you don't have to just believe me when I say how many responses there are. You can see for yourself. All right, we're at almost 100 quiz responses, so we'll leave it open for a minute longer. Uh, let's uh, um, let's look at some of these questions, these good questions that are happening on Slack. So somebody asks, let's say there's processes P1 and P2, and let's say that an event happens on P1. So let's actually draw this. I'll switch back to the document camera. Okay, so let's say we have an event on P1. The Lamport clock of that event is 1. And then you have events over here. And the Lamport clocks of those events are 1 and 2, respectively. Okay, so we'll call this event A, and we'll call these events B and C. So in this case, so the question is, so the Lamport clock of C is 2, right? The Lamport clock of A is 1. So the question is, we still can't say for sure that C didn't happen before A. Yeah, that's absolutely the case. We cannot say for sure that we don't know anything about the relationship between C and A in terms of happens before. So especially because these processes haven't communicated at all. And these processes don't share a clock. So we don't know anything about whether C happened before A. A could have happened before C. Okay, so the question is asking, it's asking about that contrapositive thing. So okay, yeah. So we know. So in this case, so contrapositive says this, right? It says that if LC of A, if it's not the case that the Lamport clock of A is less than the Lamport clock of B, then it's not the case that A happened before B. Um, but that's true here, right? So here, indeed, it's not the case that the Lamport, so I guess if the events here, which events do we care about? C and A? So the Lamport, maybe we want to substitute in some other like P and Q here, just so that we don't get our identifiers confused. So if the Lamport clock here for, I guess, event C, it's not the case that 2 is less than 1, right? So it's not the case that the Lamport clock of C, which is 2, is less than the Lamport clock of A, which is 1. Okay, so the premise checks out. And that should imply that that it's not the case that C happened before A. And that checks out also. It is indeed, it's not the case that C happened before A. Or we don't know that C happened before A. Okay, so I guess the question is like, well, what if C did happen before A in terms of wall clock time? Okay, yeah, I mean, maybe it did, but it didn't happen before A according to the happens before relation. And the happens before relation is kind of all that we have to go on, right? So if there were some way to play God, right, and have some sort of global clock for this whole system and know exactly when each event happened according to that global clock, then we could figure out, okay, C happened before A or A happened before C, but whatever. But no such global clock exists. So the only tool that we have for reasoning about what happened before what is this happens before relation. And it's and the happens before relation tells us that it's not the case that we know that it's not the case that the happens before relation tells us that C happened before A. So if you're wondering if this is kind of a weak tool, yeah, I would agree. Lamport clocks are kind of a weak tool, and that's why we want something better. We want something that will actually give us more useful information, and that's what vector clocks are for. So we're almost out of time for today. But next time we're going to talk about vector clocks. And so vector clocks are actually going to give us the other half of that implication. So we saw that Lamport clocks are what we call consistent with causality, but they don't characterize causality. And vector clocks are actually going to give us both of these properties. They're both consistent with causality and they characterize causality. And so we don't have time to talk about that this time, but we'll pick that up again next time. So see you then.